welcome to the lesson on component vectors. So continuing on with our vectors topic. So component vectors, you might have a background in from previous lessons. So as mentioned in an earlier lesson, if the vector is expressed in the form of something, we call it a component vector. So if it's expressed in the form of something starting with C, that's right, it's a column. So as mentioned in an earlier lesson, if the vector is expressed in the form of a column, we call it a component vector. For example, here we go, x and y. So we see it's expressed in the form of a column. So that's an example of a component vector. The top number, the number that would appear here, represents the something movement, and the bottom number represents the something movement. So you might remember that the top number represents the horizontal movement, so sideways movement, and the number here represents the vertical movement, up and down movement, so horizontal and vertical movement. Here's another example of a component vector. It's expressed in the form of a column. So -2 and 6, so it means a movement of how many units vertically and how many units horizontally. So I've tricked you and just swapped it around. So remember, x first, then y. So the vertical movement is the y movement. So it's 6 units vertically. You could put +6 if you want, or you could just write 6 because it implies positive if you just write 6. And how many units horizontally? It's -2. So you must have -2 units here. So +6 units vertically and -2 units horizontally. So meaning it's moved up 6 units and back 2 units. Or you can think of it as back 2 units and up 6 units, same thing. Let's do some more examples. So we've got the vector. So here it's got a little coordinate plane. We've got the point C. And they're saying that the vector CD is -2, -3. So this is an example of a component vector. So this is the horizontal movement and this is the vertical movement. So mark and label the point D in the diagram. So they don't want you to draw the vector. Be aware of that. They're not asking you to draw this vector. They're asking you just to mark the point D. So in going from C to D, you go back by 2. Oops, sorry. You go back by 2 and down by 3. So from C, go back by 2, down by 3, and they just want you to mark in point D. So just be aware of that. They didn't want you to draw the vector CD. They just wanted you to mark in point D. Mark and label the point D on the diagram. And then finally, write the coordinates of D. So D's here, so its x coordinate is 3, its y coordinate is 2. That's easy enough. Just checking that you're following the instructions carefully there, that's all. The vector EF is -2 and 5. Here's a component vector. Mark and label the point E on the diagram. So notice that where F is the finishing point. So where would E be if you went down 2 from E, sorry, backwards by 2 from E and up 5. So noticing here, note that this is the second letter. So this is the second letter, meaning it's beforehand. Oops, beforehand we gave you the first letter. That was the first letter. But now we've plotted the second letter. So you've got to think, okay, so EF, if it helps, EF is -2/5. Maybe think of what would FE be. So FE would be +2, -5. So FE would go across 2, down by 5. That's a way of thinking about it. So you do the negation of this. So you could write FE, vector FE is 2, 5. I've just written the instruction, instead of going left by 2, you'd go right by 2 and down by 5. Because the negation going from F to E would be +2, -5. So go down 2, across, so go right by 2 and down by 5. Mark, they don't want you to draw the vector again, they just want you to mark in the point E. So go right by 2, down by 5. You should hopefully end up there. Did I go down too far? No, that's fine, because I went down by 2. 1, 2, 3, 4, 5. It just looks really big on my screen. So marked and labelled the point E, didn't draw the vector. Write down the coordinates of E. Write it, what's its x coordinate, what's its y coordinate. There you go. So you can see how this kind of unit relates a little bit to coordinate geometry. Some more tricky examples. We've got vector AB. Here's AB here, which is 6, -4. Column, you can call that a column vector or a component vector. Column vector, component vector, same thing. So if you want to write in brackets component vector, that means the same thing. AB is 6, negative 4. BC is negative 1. So BC is this one. Negative 1 means go back by 1, up by 3, and so on. Write down as a column vector AC. So AC, meaning going from here to here. So you could think of, you know this one, and you know this one. AB, you know AB, and you know BC. You could think of AC as being AB plus BC, couldn't you? So the resultant vector is AC if you take this pathway, if you go AB plus BC. So I write out my little plan, vector AB plus vector BC. And then you can just pop in the component vector. So add the two vectors to get AC. So basically that's what we're saying. Add these two vectors to get AC. Plug them in because AB is this one here. BC is that one there. Then you just add the x components and add the y components. So 6 plus negative 1, what's that? Negative 4 plus 3, and what's that? Feel free to write your own answer and then just check. Did you get the same? Yes, hopefully you did. Another easy one, like we've got find double AC. So whatever AC is, they just want you to double it. So basically take these numbers and just double them, because that's a scalar multiple. So 2 is a scalar multiple. This part here is the vector. So if you want to show working out 5, negative 1, I just wrote times 2 times 2, will give you 10 and negative 2. They want you to represent that vector that you just drew on the diagram above. So notice you've got AC here. So going from A to C, going from A to C, that would be the vector AC. So double AC just means go twice as far. That's all they want you to do. So you might not have been sure what it was asking. 2AC will be twice as long as AC and begin at the same point. So they both begin at point A. So see, I just drew it there. So point A going across to C, and then go twice as long. Try to be as accurate as possible. You can use a ruler and actually measure it twice as long. I just did it roughly on here. And represent on the diagram above, so that's what we've done in yellow here. I might want to put an arrow to this diagram, just so in your notes you realize what you're referring to. Ooh, go. Another question. Here, remember we can use bold letters as well to represent vectors. So lowercase m in bold, 3, negative 4, and this vector n is negative 2 and 1. Find m plus n. Easy peasy, just add the two column vectors together. Show some working out. Don't miss out on your working out steps. 3, negative 4 is m, negative 2, 1 is n, and we're adding. So just add the x components, add the y components. 3 plus negative 2, negative 4 plus 1. Let's see if we got the same answers as each other. Hopefully we did. 3n, again, 3 is just a scalar multiple. So whatever n is, you just multiply both things by 3. Maybe show some kind of working out, good idea. Negative 2 and 1 is n times 3 times 3. And have a think what your answer would be. Write it down and see if we got the same answer. Hooray, hopefully we did. Then they just want you to draw vector m on the grid, and they don't tell you where to start from. There's no starting point, so you can pick your own starting point. So just be aware for m, you're going to have to go. M is, if it helps, write it out again. M is 3, negative 4. I just got that from here. So it means across. You could, from wherever you start from, you're going to have to go across by 3, to the right by 3, and down by 4. So you don't want to start here, for example. So you go across by 3 and down by 4, you end up off the grid. So if it helps, do it here, do it here, do it wherever you want. Just somewhere more up in this corner, I guess. So you can go across by 3, down by 4, without going off the grid. So I chose this random starting point. I went across by 3, down by 4, and then the resultant vector is in yellow here. They just wanted you to draw the vector m. You could label it bold m if you want. Remember, sometimes you can write m with a little line underneath too, as representing the vector. Cool. Another example, A is the point 43, so that's a coordinate, not a vector. And B is a point negative 212. Again, that's a coordinate, not a vector. It's not expressed as a column or anything. Whereas BC is a vector, because it's expressed in this column format. The vector BC is 3, negative 8. Write AC as a column vector. So we know point B. What we want to do is we want to find the coordinates of C. We need to find the coordinates of C first, and then we can use that to write AC as a column vector. So we've got the coordinates of A, but we don't have the coordinates of B. So what on earth do I mean by this? Just showing you. So coordinates of C, let's call C xy. So the coordinates of C could just be xy, represented as a vector, because if you take C, the coordinates of C would go here and here, the coordinates of B would go here and here, and you subtract. So these coordinates minus those coordinates can help you to get the vector, and then we can solve for the mystery x and the mystery y. So it's coordinates of C minus coordinates of B equals that column vector there. So x minus minus 2, y minus 12, and so on equals 8. So x minus minus 2 might help to write it as x plus 2. The rest is all still the same. So if x plus 2 equals 3, what does x have to be? And if y minus 12 equals negative 8, what must y be? That's what we need to think about. So C is 1 and 4, because 1 plus 2 is 3, and 4 take away 12 is negative 8. So 1 and 4 are the coordinates of C. Then they want you to therefore write AC as a column vector. So maybe let's do that over here. So AC, remember you put in the coordinates of the second letter minus the coordinates of the first letter. Second letter minus the coordinates of the first letter is how you get the resultant column vector. So AC, we've got coordinates of C here, x, y, and always minus the coordinates of the first letter, 4 and 3, because we know that one here. What's 1 minus 4? Put it here. What's 4 minus 3? Put it here. Hopefully we've got the same answers as each other. Now moving on to vector magnitude. Remember, magnitude is like the length of the vector. The size of the vector, and graphically it's represented by the length of the vector. Because all vectors have magnitude and direction, whereas scalars only have magnitude. They don't have direction. So the magnitude, in some other books they might call it the modulus of the vector. So the magnitude modulus of the vector, OA, is a vector OA, is represented by the length of OA. So just pointing out that the magnitude is the length of the vector, and is denoted by these two little sideward things here. So OA with the arrow above it means the vector OA. If you put these two little, like, looks like absolute value kind of like notation, doesn't it? But in this case it's not absolute value, it just means the magnitude. If we're talking about vectors, these two lines don't mean the absolute value, they mean the magnitude of the vector. So in this example, so we've got OA here. So O is the origin, of course, in that case, as you can see, as it's graphically demonstrated. Coordinates of A are 4 and 2. So if we want to know what's the length of that. So we know this length here is 4, because it's got an x-coordinate of 4, and we know this length here is 2, because its y-coordinate is 2, and it generates a right-angled triangle. So we can use a formula. What formula is this, and who does it come from? Ooh. Do you recognize this person from around 500 BC? Greek, holding a pyramid? That's right, it's Pythagoras. So Pythagoras' theorem can be used to solve for the magnitude of the vector, because the magnitude of the vector is just the hypotenuse of the triangle, and we know that one leg is 2 and one leg is 4 because it starts at 0, 0. So Pythagoras' theorem, a squared plus b squared equals c squared. So basically the magnitude of the vector is the c. So the magnitude is the c, so we're saying the magnitude of the vector squared equals a squared plus b squared. So 4 squared plus 2 squared. And 4 squared plus 2 squared is 16 plus 4, which is 20. And then remember, to solve for the magnitude, you therefore have to square root both sides. So the magnitude of the vector must be the square root of 20. And remember your surds, 20 is the same as 4 times 5. So to simplify that surd, 4 is a square, so you would square root the 4. So square root of 4 times 5 equals 2 root 5. So this is the magnitude of this vector here. It's the length of that vector. We use Pythagoras' theorem to solve for it, and then we just simplify the third. So reminding us that vectors can be represented with capital letters. These are not in bold, they're just meaning from point O to point A, point O to point A, and that line represents the vector. Vectors can also be written as lowercase bold letters, which you know already. For example, instead of OA, you could write V, bold V for vector. Just reminding you that when writing vectors by hand, like on paper, instead of like on print here, you can underline the letter V instead to indicate that it's a vector. Because it's hard to draw the bold on an exam, so you could just write V and put a little line under it. It means the vector V. So let's try an example. Given that vector A, it's kind of in bold, equals 4, 5, it's a component vector, find this thing. And what is this thing again? That's right, it's the magnitude of A. So solution. By this symbol of A, we mean the length of vector A. So the magnitude, we mean the length of the vector A. To find this out, we use Pythagoras' theorem. So remember, just remembering in general, A, B are the legs. They form a right angle, and C is the hypotenuse. A squared plus B squared equals C squared, but in this case, A is different. A is the hypotenuse. So our vector is 4, 5, so it means across by 4, up by 5. So from the starting point, you'd go across by 4, up by 5, which indicates that it's got legs of 4 and 5. So A is like the hypotenuse in A squared plus B squared equals C squared, so we just use Pythagoras' theorem. Making the hypotenuse the subject, I'm just going straight to saying the square root of. Square root of 4 squared plus 5 squared. 4 squared is 16, 5 squared is 25. 16 plus 25 is 41 units. So square root of 4, and it's the square root of all of those. So if this third, 41 is a prime number, so the third doesn't simplify anymore. You can just say square root of 41 units is the magnitude of A, which is formally the length of A, vector A. Another example. Given that lowercase u equals this one, v equals that one, and that vector equals this one. Notice p is unknown. Find the magnitude of u. So magnitude of u, you've got one leg here, you've got the other leg here. You can just Pythagoras that thing. So the length of the vector using Pythagoras is what it's asking for. So notice I use Pythagoras' theorem. It's always a hypotenuse in this case, I guess, if it's a diagonal. So square root of 6 squared plus negative 8 squared. The negative 8 has to be in brackets, because if you don't put it in brackets, negative 8 in brackets squared means positive 64. Negative 8 squared without brackets means negative 64. So 6 squared is 36. Negative 8 times negative 8 is positive 64. Add these two together, you get 100, and you're square rooting the answer. Square root of 100 is 10. So notice I'm writing units, because on coordinate geometry, the lengths are in units. So the magnitude of vector u is 10 units. So don't forget to write that down there, 10 units. Then they just want, so there was a magnitude question here. They just want you to do a few operations. Basically, what's scalar multiple of 2, what's double this one, plus that one. That's all they're asking. So to show working out, I just put the first vector times 2 plus the second vector, and then show a bit more working out. 6 times 2 is 12, negative 8 times 2 is negative 16, plus the other vector, 12 minus 9, negative 16 plus 10. I think what those little answers are. There you go. It's 3 and negative 6 when you do that operation there. Given that vector w is parallel to the vector u, so they're saying that this vector is parallel to that vector. Calculate the value of p. So remember from a previous lesson, for two vectors to be parallel, one must be a scalar multiple of the other. So whatever you multiply this by to get that, you multiply that by the same number to get that. So you could work out what you multiply by doing 15 divided by 6. And yeah, as I said, two vectors are parallel if one is a scalar multiple of the other, meaning that whatever you times this by to get that, you multiply that by the same number to get that. So, the way we're saying 6 negative 8 multiplied by what scalar multiple will give us 15 and p. So we know 6 becomes 15, so we can think 6 times what equals 15. And it turns out 6 times 2.5 equals 15. If you're having trouble seeing that, just do 15 divided by 6, do the reverse step. 15 divided by 6 is 2.5. So that question mark, the scalar multiple is 2.5. So therefore, to work out what p is, take the negative 8 and multiply it by the same scalar multiple. Negative 8 times 2.5, I think what that is. There it is. Negative 20. Yep, let's keep going. Examples. Vector AB is that, vector BC is this, and vector CD is that. Find DA. So DA, we've got A to B, then B to C, and then C to D. So what you might want to do is, you could work out AD easily, because if this was a picture, like, you know, going from A to B, going cross 2 up 1, so it goes like that. B to C, going down by up by 2. C to D, going down back by 5, up by 1, and so on. So to work out DA, you could work out AD first by just adding those 3 vectors together. Because to get from A to D, it's like going from A to B to B to C to C to D again. So AD first, AD is just that plus that plus that, because going from A to B to B to C to D is the same overall as if you just went straight from A to D. So set it up, show you're working out, add up your X components, add up your Y components. Then hopefully you get negative 3 and 4. And then don't forget that once you've got AD, just don't be aware that they want DA. So remember, DA is just the negative of AD. So you just change the signs on this. So the negative of this would be positive 3 over negative 4, which ends up being our answer for DA. Then what are they asking for here? That's right, they're asking for the magnitude of your answer. So you can just use Pythagoras' theorem, go straight to working out the hypotenuse. This is the length of the vector DA using Pythagoras' theorem. So DA, magnitude of DA, equals square root of 3 squared plus negative 4 squared. Again, you've got to have brackets around the negative if you're squaring or cubing or anything like that. Otherwise, you get a different answer. 3 squared equals 9. Sorry, I got hair on my mouth. 3 squared equals 9. And negative 4 times negative 4 is positive 16. 9 plus 16 is 25. Square root of 25 is 5 units. And the reason why I bothered to write 5 units is because we're talking about a magnitude, which is a length. Whereas if we're talking about a coordinate, you don't write units. And thank you very much. That's the end of the lesson.